I want to talk about the p-test, which is a test we originally learned for integrals and will also work for series. The setup is we have a very particular kind of series, looks like this. So the number n, that's changing, but it's always being raised to the same power. P isn't changing. Now this series is going to converge when p is big enough, and it's going to diverge when p is smaller. So this is going to make a lot of series be pretty easy to determine convergence or divergence. So for instance, 1 over n cubed, that's a big number, it's going to converge. That high number in the denominator means I'm getting big numbers fast in the denominator. So the whole term that I'm adding, 1 over n cubed, it's getting very small very fast. What about this one, 1 over n to the 0.2? Again, I have this form of n to the constant. Since 0.2 is small, the denominators are getting big, but not that big. These things that I'm adding are not getting tiny fast enough. This is going to diverge. As I add more and more and more terms of this series, even though the things I'm adding are getting smaller and smaller, my sum is going to keep growing without bound. It's going to get unimaginably huge. P-series is also really useful because oftentimes we want to do a comparison. So let's think about something like this, 1 over log n. Now this isn't a P-series, but I claim I can compare it to a P-series because log n is smaller than n. So that means 1 over log n is bigger than 1 over n. And I know that this diverges because it's P-series. P is equal to 1. And since this diverges, that means I start adding these up, and the more of them I add, the bigger my sum gets. My sum is growing without bound. This one is even bigger. If I add the same number of terms, this 1 over log n is going to give me an even bigger number. So since the bottom series diverges, it adds to a bigger and bigger and bigger number without bound, the top series has to be doing the same thing as well. So that tells us this is going to diverge.